Hey folks, let's just start with a basic question. What is light? This may be a review to many of you, but it's always good to go back and refresh our memories as to its very nature. So, we now know that light can be described as oscillating electromagnetic radiation. And by oscillations, what we mean is that we have these waves, these sinusoidal waves as depicted in this diagram here, representing light itself. Now, the light itself, and this was something that was only determined at the end of the 19th century, consists of electric fields and magnetic fields. The electric field represented in this diagram by the blue wave that is directed upwards, and the red represents the magnetic field, and we'll note that the electric field and the magnetic field are perpendicular to each other. So this is what we refer to as the wave nature of light. The fact that light is a wave was determined through some of its basic properties that we know are properties of waves themselves. So, for example, we have something called interference effects, which is characteristic of waves. Now, in this particular diagram, we'll note that on the left side, we have a water wave where there are two sources of these waves that propagate outward, and as these two sources propagate outwards, the waves interfere with each other, such that in these particular low areas, the waves cancel, and that's because of interference between the two. So that is something that's characteristic of all waves, characteristic of water waves, sound waves, and we see the same pattern when we look at light in what's referred to here and diagrammed as the double slit experiment, where light waves are passing through these two small holes, and those represent sources, and as the waves propagate beyond the holes, we'll note that we get interference, and we see what's called an interference pattern associated with this. When the waves interfere such that they're in phase, they add together, and we'll see the two waves here, for example, in this little diagram, add together to give a bigger amplitude wave, and that is something that yields in the pattern bright spots in these patterns where they interfere in a way to add to the intensity. And then they can also be out of phase, and when they're out of phase, the waves cancel each other out, and we see these dark patterns. So we see that in light when we pass it through this double slit pattern and generate these patterns which have alternating bright and dark spots. That is characteristic of waves. It's not characteristic of particles because, as you probably would surmise, particles passing through two holes would just form two patterns on the wall where the particles hit the particular wall in this situation. So this alternating pattern of bright, dark is characteristic of all waves, just as we noticed over here with the water wave. When the waves interfered in a positive way, we had a larger amplitude, but in a negative way, they cancel each other out. When they interfere in a positive way, that's called constructive interference when the waves are in phase. When they're out of phase and cancel, that's referred to as destructive interference. So again, this is something we see in all waves and something we see in light. So for that reason, we know that light behaves as a wave. All right, so let's look at a couple of other examples. Here's an illustration which shows the pattern of laser radiation and interference effects. And lasers are something that we'll talk about in a later video. But in this case, we have two different lasers. We have a red laser here. And again, we see this alternating pattern of bright, where we have constructive interference, and dark, where we have destructive interference. So it's bright, dark, bright, dark, bright, dark. So this is a single laser beam passing through a source, a slit kind of situation that generates this pattern of alternating pattern of bright and dark. So there's an interference pattern. In the lower illustration, we actually have a green laser, and this generates a circular, in this particular setup, a circular interference pattern where it's very bright in the middle, and then we see this dark ring outside. Again, that alternating pattern is something that corresponds to interference. So clearly, light behaves as a wave. That's all there is to it. All right, so let's talk about some of the properties of waves. And so here we have this diagram which shows two different waves. We'll first describe the wavelength of a wave. All waves have a wavelength, and that wavelength is just the distance between two crests of a wave. And we also have something, and actually let me point out that the symbol that we're using here is the Greek character lambda that we pretty much universally use to represent the wavelength of a wave. And then we also have something called the frequency, which is the number of waves that would pass by a fixed point in 1 second. So when we talk about waves, we talk about the wavelength of the wave and the frequency of the wave. Now the frequency characters is a Greek character nu. It kind of looks like a V, but not quite. So we will pretty much use universally the lambda corresponding to wavelength and the frequency corresponding, or nu corresponding to the frequency of a wave. Now the two different waves here, we'll note that we have the top wave, the red one, corresponds to a much longer wavelength than the purple one in this situation, and so therefore we'll note that we have that distinction between the two. But we'll also note that frequency and wavelength are inversely proportional, so when we have a longer wavelength, we're going to have a lower frequency. So the bottom wave has a shorter wavelength but a higher frequency. They are, of course, related mathematically to each other through a very simple relationship that's characteristic of all waves, and that is the wavelength times the frequency is equal to the speed of propagation of that wave. And this is a relationship for all waves, water waves, sound waves. The wavelength times the frequency is equal to the speed of the wave. Now, in the case of light, the speed is represented by c, which is the speed of light itself, which is 2.998 times 10 to the 8 meters per second. Now, I will point out in units that when we talk about the units of a wave, we'll note that, of course, wavelength is going to have units of length, and in SI units, that means that the wavelength would be in meters, although we won't always be using meters. Sometimes we'll be using nanometers or millimeters or picometers, depending on the type of wave that we might be talking about. And that frequency, represented by nu, is going to have units of inverse seconds, also referred to as hertz in that situation. So we will note, as we noted before, this inverse relationship between the wavelength and the frequency, so that a longer wavelength is going to correspond to a lower frequency. And again, this is characteristic of all waves, sound waves, water waves, and of course what we're talking about here are light waves. All right. So we have electromagnetic radiation oscillating, and we have this spectrum here that shows the different types of electromagnetic radiation and the frequencies and the wavelengths corresponding to those different types of radiation. We'll note over here on the high frequency side, we will have gamma rays and X-rays, which are lower frequency than gamma rays. We'll notice that on the left side, with the higher frequencies, we also have the much shorter wavelengths. So when we talk about gamma rays with, say, something on the order of 10 to the 22nd hertz, then we might be talking about wavelengths, very small wavelengths, on the order of 10 to the minus 14, 10 to the minus 13 meters. Visible light, as shown down here, corresponds to a very small region of the electromagnetic spectrum. On the high frequency side of visible light, we have ultraviolet, and on the low frequency side, we have infrared. The visible light itself is shown here, and the corresponding wavelengths ranging from, in this case, 390 to 750. Usually we say that visible light represents a 400 to 700 nanometer range. And of course, visible light corresponds to that region of the spectrum that our eyes are sensitive to, which, of course, from an evolutionary perspective, is simply due to the fact that our sun has its greatest intensity output in this region of the spectrum. So that corresponds to visible. We'll also note, of course, that different colors correspond to different wavelengths. So on the short wavelength end, we have violet, and on the long wavelength end, we have red corresponding to that. So this is, of course, Roy G. Biv, red, orange, yellow, blue, indigo, violet, corresponding to the electromagnetic spectrum. So again, remembering 400 to 700 nanometers roughly for the visible region of the spectrum, and of course you'll also note that that's a very, very tiny region of the entire spectrum, which ranges from gamma rays all the way down here to radio waves. Radio waves corresponding to low frequency, very high wavelength. So we might be talking about 1,000 or 10,000 meters corresponding to the wavelength of these electromagnetic waves. So again, light behaves as a wave. We have interference effects. Light has a wavelength. Light has a frequency. Yay! But is that all there is to it? Well, it turns out around the beginning of the 20th century there were some experiments and some observational phenomena that made physicists begin to question the nature of the wave itself. Now, we're not going to talk in detail about these phenomena in this video, but just to lay out some of the specifics, we have something called black body radiation, which is basically the color that an object glows as you heat it. And the only explanation for that that was developed by Max Planck and presented in 1900 seemed to indicate that the energy output of radiation was dependent on the frequency of the electromagnetic radiation of the wave, which is not a property of waves. The energy of a sound wave or a water wave is related to its amplitude, not its frequency. So that was very unusual. And then there was the photoelectric effect, and the theory for that was developed by Albert Einstein in 1905, which was the year that he's published 4 seminal papers for the development of physics. Of course, one of those had to do with special relativity. And so again, here we had a situation where the energy output seemed to be dependent on the frequency of the wave and not the amplitude or intensity of the wave. And then there was atomic spectra, and atomic spectra we know has discrete lines. You know that from taking various chemistry classes. Spectroscopy, of course, is a powerful tool that we use for the identification of substances, and that's due to the fact that each substance has a fingerprint of discrete spectral lines. Now, again, that was something that couldn't simply be explained by the concept of light behaving as a wave. And so then we have to ask the question, does light consist of a collection of particles? Well, it behaves as a wave. How can it consist of a collection of particles? So we have to introduce something here that is a little bit confusing and confounding, and that is that this concept of wave-particle duality, that light will behave as a wave under certain circumstances and behave as a collection of particles under other circumstances. And again, we'll get into this in a little bit more detail later on, but right now we have this situation where we have wave-like properties where the light has a characteristic wavelength and a frequency, but it also has particle-like properties where the particles depend on the frequency of the light. And so this led to the Planck equation, which you've no doubt seen before, of E equals h nu and nu being the frequency of the light, and h being what we now call Planck's constant, which is a very, very small number, but it is the proportionality constant to determine the energy of the wave at a particular frequency. And we will note in this that from this equation that the energy is proportional to the frequency. So as the frequency increases, the energy of the wave increases. All right. And that because frequency is inversely proportional to the wavelength, we'll note that energy is therefore also inversely proportional to the wavelength. So as the wavelength increases, the energy decreases. Now, so this is the energy corresponding to these particles of light, which you now know we refer to as photons. Photons, of course, are particles of light. This term was coined by G.N. Lewis, our favorite chemist, in the 1920s. So photons have an energy equal to h nu, proportional to the frequency. So higher frequency photons are going to have higher energy. And that gets us back to our spectrum here, where we will note on the left side of our diagram where we have higher frequency, that means we have higher energy. And so gamma rays are very high energy very high energy electromagnetic radiation, and the gamma rays are emitted in nuclear processes. X-rays, also very high energy, but not as high as gamma rays. Then ultraviolet light is higher energy than visible light, and ultraviolet light, of course, is what we are concerned about when we talk about exposure to sunlight. Overexposure to ultraviolet light, higher energy ultraviolet light can rupture chemical bonds. Lower energy ultraviolet light causes electronic transitions, and these can damage the DNA, and of course overexposure to sunlight can lead to cancer, and that's because of these ultraviolet photons being higher in energy. And of course that's also a concern we have about the depletion of the ozone layer and the atmosphere and the stratosphere. Ozone helps to block high energy ultraviolet rays. The higher frequency ultraviolet rays are blocked by the ozone layer, but if we deplete the ozone layer, that means these higher frequency photons get through, and because they're higher energy, that can cause more damage to molecules that and rupturing chemical bonds that can lead to all kinds of issues with biological systems. So this ends our basic discussion of light. What is it? Is it a wave? Is it a particle, a collection of particles? Well, it depends on what we're observing. Sometimes it will behave as a wave, sometimes it behaves as a collection of particles, and we will certainly need to keep both of those in mind as we move forward and talk about chemical systems. Thank you very much.